Alright, so this is our Chapter 3, Section 1 lesson video for chemistry. And so in Chapter 3, we're going to focus on measurement. Now, in the beginning, I'm going to show you some things, and you're going to, some of you may know an easier way to do them, or you've heard something different from another teacher. If you really accept the process, the easier you can get through Chapter 3, the easier when we get to the math for the second part of the class, the easier that will be also. So just pay attention and just follow the process, and hopefully it won't be too painful. Alright, so a measurement is a quantity that has both a number and a unit. So like 3 is a number, 3 meters is a measurement. A unit typically used in the sciences are those of the International System of Measurements, or SI units, and so we'll talk about those in Section 2. In scientific notation, a given number is written as the product of two numbers. There's a coefficient, and it is 10 raised to a power. So the product, of course, means they're multiplied. So 6.5 is the coefficient times 10 raised to the power of 7. In scientific notation, the coefficient is always a number equal to or greater than 1 and less than 10. So in other words, there should only be one digit in front of the decimal. So like we couldn't have 16.5, or we couldn't just start with 0.5, one digit. So how do you figure out how to do this? Well, I'm going to show you, but this is just an example at the bottom. So your coefficient comes from the numbers that are not zeros. So we get a 6 and a 5. And then if you don't see a decimal at the end of a number, then it's at the end. Okay, some numbers you'll see the decimal. And so you just count over until you have one digit in front of the decimal. So I go 1, 2, 3, 4, 5, 6, 7. So it becomes 6.5 because I moved my decimal here, times 10, and since I moved it 7 places, it's to the 7th power. Okay, so let's practice some of these. Some of you may have already learned this before in another class. Alright, so it says, write the following numbers in scientific notation. So my answers are going to kind of come up here, so I'm going to write my answers over here. Alright, so it says, write it in scientific notation. Well, if you don't see a decimal, it's automatically at the end. So I'm going to put my decimal right here. I want to move it where there's one non-zero digit in front of it. So I start at the front of my number. 3 is a non-zero digit, so that means I want to move it right here. So the whole point of scientific notation is if you have a really large or really small number, you don't have to write all these zeros. But you do want to keep most of the numbers. Alright, so what I'm going to do is I'm going to keep the 3.94. And I put my decimal there because that's where I decide to move my decimal. Then I have to figure out how many places did I move that decimal. So I do times 10, and then I just count. 1, 2, 3, 4, 5, 6, 7. So it becomes times 10 to the 7. Now, if there was a unit on here, so pretend like this said, liters at the end. You put your unit at the end. I have a lot of students who try to put it right here. Put your unit at the end of this number just like you would a normal number. Alright, so that's one example. Alright, so let's look at another example. We have 2,800. So where's my decimal to begin with? If you don't see it, it's at the end. Alright, so I want one non-zero digit in front of the decimal. So I'm going to start at the front. 2 is a non-zero digit, so I'm going to move my decimal right here. And again, we're trying to get rid of all these extra zeros, so I'm going to change my coefficient to 2.8. And then I just count over to see what my power is going to be. So 1, 2, 3. So it's times 10 to the 3. And if I had a unit, I would put my unit at the end of that number. Alright, so that's what it looks like if you have a large number, or a number greater than 1. Your power is positive. But sometimes you have a really small number that's less than 1, like you see the decimal in the front of the number. In that case, we're going to count in the opposite direction, so that changes our power to negative. Again, I know a lot of you probably learned this in physical science, so hopefully this is just a review. Alright, so here's my decimal right now. I want one non-zero digit in front. Well, right now I have a 0. That doesn't count. There's still a 0, still a 0, still a 0. I want it after the 5. Because see, now there's one non-zero digit in front, the 5. So my coefficient becomes 5.67. Now notice, in these two examples, we were counting to the left because our numbers are really big, they're greater than 1, so our exponent is positive. In this example, we're counting the other direction, 1, 2, 3, 4. So in this example, because our number is very small, it's less than 1, our exponent is negative. So I counted over 1, 2, 3, 4, so that becomes a negative 4. Just like that, all right? So in our last example, again, I have a really small number, so I can go ahead and decide that my exponent is going to be negative again. So I have my decimal right here, but I want one non-zero digit in front. So hopefully you're getting that part, so I want to move it right here. So see, there's one non-zero digit to the left of the decimal. I call it in front. I know that confuses some of y'all, so we can say to the left of the decimal. All right, so that means my coefficient is just going to be 2. You can put 2 in a decimal point if you want to. All right, and so then I just count over. 1, 2, 3, 4, 5, 6, 7. And so this becomes times 10 to the, now this is a really tiny number, so my less than 1, so my exponent is negative, so it becomes to the negative 7. And if I had a unit, I would put it at the end. All right, so if you have a large number where your decimal is after most of your numbers, then that's going to have a positive exponent. If you have a really tiny number, less than 1, then your exponent is going to be negative. And that's how you do that. A lot of people, they get confused and they think that you can just count the zeros and that tells you what your exponent is, but you're not counting zeros, you're counting decimal places that you move. So you even need to count it if you're moving it past non-zero digits. All right, so let's look at going the opposite. Sometimes I'll give you scientific notation, but we need regular notation. All right, so we have 3.22 times 10 to the 4. So what I like to do is I just like to start with my coefficients. I have 3.22. All right, times 10 to the 4. So 10 to the 4, that's a positive number. So that means it's going to be a big number. And by big, I mean greater than 1. So if the number is big, would I want to put zeros in front of it or zeros behind it to make it big? Well, we want zeros behind it to make it big. So how many places do I move it? I move it 4. I don't add 4 zeros. I move it 4 decimal places. So I go 1, 2, 3, 4. There's my new decimal place. And then you just fill in zeros. And if there was a unit, you put that at the end. Now, this is my pet peeve, so if you're not in my class and you're watching this, your teacher might not care. My pet peeve is I don't want you turning in an answer with more than 1 decimal point. Okay? So if this is the way your answer looks, I will mark that wrong. You have 2 options. You can either rewrite it, and you don't even need the decimal point at the end, but if you want to put it, that's fine. Or you just need to erase the one you don't want me to see. Okay, either one is fine. And again, you can have that decimal point, you don't have to have that decimal point, it doesn't matter. All right, so let's look at the next one. So it's 2.1 times 10 to the negative 5. So I'm going to start with my coefficient, 2.1, and this is to the negative 5. So negative means it's going to be a small number. So if it's going to be small, and the reason that I emphasize big and small numbers is a lot of my students, if they try to memorize left and right, because up here it's kind of backwards from down here, so it gets kind of confusing. So if you'll just remember big and small, then you won't get confused as easily. All right, so it's 10 to the negative 5, so I want a small number. So would I want to put zeros in front to make it small, or zeros in back? Well, if I put zeros in back, that's going to make it large. So I want to put my zeros in front. So how many places do I move it? Well, I move it 5. So 1, 2, 3, 4, 5. There's my new decimal. I fill in my zeros. And then, of course, you have 2 options. You can erase that decimal point that you don't want me to see, or you can rewrite it. Now, when it comes to the decimal point in front, the 0 in front of that is optional. If you want to put the 0, you can. If you don't, you don't have to. I usually put the 0 in class just so that you can make sure to know that there's a decimal point there, because sometimes it's hard to see the board. All right, and again, if there was a unit, you'd put that at the end. All right, so let's look at our next one. So we have 8 times 10 to the 2. So I'll put my 8. 2 is a positive exponent, so that means it's going to be a big number. So my decimal point, you don't see one right now. If you don't see one, where is it? It's at the end. So it's 8 and then the decimal point. All right, so it's times 10 to the 2. So to make it bigger, am I going to put zeros in front or zeros in back? Well, to make it bigger, I'll put zeros in back. So how many places do I move it? Well, it's to the 2, so I'm going to move it 2 places. Put my new decimal and fill in my zeros, so it becomes 800. And so again, don't turn in a number with 2 decimal points. So I would either erase this one or just rewrite it as 800 or 800 with a decimal. It doesn't matter. All right, and then last one, we have 7.90 times 10 to the negative 6. So I'm going to start with my coefficient, 7.90. 10 to the negative 6 is negative, so that means my number is going to be small. So to make this number small, do I want zeros in front or in back? I want zeros in front. So how many places do I move it? I move it 6. 1, 2, 3, 4, 5, 6. And then I fill in my zeros. All right, so again, don't forget, don't turn a number with 2 decimal points, so I can either erase that one or I can rewrite my number. All right, and again, the 0 in front is optional if you just want to put 0.0000790. Hopefully I said enough zeros there. It's fine. That's fine too. And remember, if I give you a unit, you need to put your unit at the end. In this one, I didn't give you any units on those. All right, so like I said, hopefully you're remembering this from physical science or another class, and hopefully this is review. So let's move on to something that might not necessarily be review. So the next thing is the difference in accuracy and precision. A lot of people use these interchangeably, and they are similar, but they're a little bit different. So accuracy is a measure of how close a measurement comes to the actual or true value. So let's say you're measuring the mass of a wooden block, and the actual value is 5 grams. Your accuracy depends on how close you get to 5. So like if you get 5.02 grams, that's pretty accurate. If you get 7.9 grams, that's not very accurate. Precision, on the other hand, is a measure of how close a series of measurements are to each other. Because in science, it's not just about getting the right answer once or being accurate once. You want to also be precise. You want to be accurate over and over and over again. If you create a diet pill, it doesn't matter if it works for one person one time. Who's going to buy that? Okay, you need to get a huge group of people of all different genders, ages, all that kind of stuff, and have all of them take it, and you need to show that you're not just accurate once and one person lost weight. You need to show that it happens over and over and over again. So of course a lot of books use a bullseye. So in a bullseye, the center is what you want to hit. That's our true or accurate value. All right, so here they're accurate and precise because we hit the bullseye, that's the true value, and we hit it 3 times. Here we are pretty precise because if you look, we're hitting in the same spot. And I know it's probably hard to see on the camera, but these 2 are kind of outside, right outside of the bullseye. So they're precise, they're all near each other, but it's not as accurate because we only hit the bullseye 1 time instead of all 3. And then this one, if you look, none of them hit the bullseye, so it's not accurate. And we didn't even get in the same spot, so it's not precise either. All right, so that's the difference in accuracy and precision. Accuracy is how close you are to the true value. Precision is, can you get a repeated result? All right, and it is, you do have the ability to be precise, get the same result over and over again, but still not have the right answer. A lot of y'all, you do that in class if you're working on a math problem. You might keep getting 24, but keep coming to me and I say, sorry, the answer is 168. So you were precise, you kept getting 24, but it still wasn't accurate. So you really want to be both in science. All right, so the next thing we're going to talk about is error. So there's 2 formulas. I will give you a formula sheet on the test, so you don't need to memorize formulas. So the first one is error. Error is your experimental value minus your actual value. So actual value is sometimes going to be called accepted value, so I tried to use both terms in my PowerPoint just so you're used to seeing. So the accepted or actual value is the correct value. So that's what the object actually is. So if you're taking the mass or something like that, that's its actual mass. The experimental value is the value measured in the lab. So it'll tell you like a student measured it, or you may actually measure it in lab or something like that. So error is just experimental minus actual. Now when you subtract 2 numbers, You can get a positive number, you can get a negative number. So error can be positive or negative. It just depends on, did you get too high of a number or too low of a number. Percent error, on the other hand, is the absolute value. So I know you've learned this in math. Absolute value means what comes out of that absolute value, those absolute value bars has to be positive. Of the error divided by the accepted value. So it's the absolute value of your error, which is experimental minus actual, over your actual or accepted value times 100. Now on this one, because we have the absolute value, percent error cannot be negative. It has to be positive. All right, and so you'll see me write it like this a lot of times in class. It's the experimental minus your actual or accepted, the absolute value of those, because that's of course your error, over your accepted times 100. And that's all you have to do. So error can be positive or negative, percent error has to be positive. And your unit for percent error is percent. So we're going to learn lots of percent things in this class, percent error, percent composition, percent yield, all of those kind of things. All of them have the unit of percent. I'm super, super big on units, so make sure you have a unit with your answers. So let's look at an example. So it says a block of aluminum has a mass of 147.3. So it's telling me that is the mass. So would that be the accepted or the experimental? Well, that would be our accepted or actual. So I'm just going to put an A above. A student measures the mass of the block as 138.9 grams. So since a student did this, this is my E or my experimental. So it says, what is the student's error? So error is experimental minus your actual or accepted, so then I just plug in. So my experimental is 138.9 grams. My accepted or actual is 147.3 grams. And so once I subtract, I get negative 8.4, and my unit is grams, because grams minus grams gives me grams. And so is it okay that that's negative? It sure is, because it's just error. Okay, so that means that since it's negative, the student got a number that was too low. It was lower than the actual or accepted value. So next, it says, what is the percent error? Well, percent error is the absolute value of your experimental minus your actual over your actual times 100. Now, since we already calculated E minus A, or our error, we can just put that in the absolute value if we want to, or you can just do your 138.9 minus 147.3 in your absolute value. It's up to you. Okay, since I already know my error, I'm just going to plug that in right here. So my percent error is my E minus A, which we already did that, negative 8.4 grams. I'm going to put that in my absolute value bars, so I remember that has to be positive, over my actual, which is 147.3 grams times 100. So if you look, your grams actually cancel this time. All right, so we're going to do an 8.4 divided by 147.3 times 100. And remember, I'm not going to do it negative because of the absolute value brackets. And so once you do that, you should get about 5.70. Since grams cancel, some of you may be confused over what the unit is. Remember, it is percent. And it is not okay for that number to be negative. All right, and so that's all you do for these. So error is just E minus A. Percent error is absolute value of E minus A over A times 100. Error can be positive or negative. Percent error has to be positive, and percent error, the unit is percent. Oh, forgot to erase my and E. Alright, so the next thing we're going to talk about is significant figures. Now, significant figures, this is the one time in the year that I'll tell you if you don't understand, you can follow the rules and you'll still get the right answer. But I would prefer that you actually understand why we use them. So, the significant figures in a measurement include all of the digits that are known plus a last digit that is estimated. So it says plus a last digit that's estimated. That means you get to estimate one place. So, if I'm measuring this piece of wood, okay, I can see that it's clearly not 1, it's clearly not 10, maybe it's about 5, so that's my estimated number. I can say it's about 5 centimeters. I I can't just say, oh, I think it's 5.6924870. I can't estimate all those places. I get one place to estimate. So if I had a better ruler, I could go out a little further instead of just, oh, it's about 5. So here they gave me more increments to measure with. So on this one, I can see, okay, well, it's definitely more than 5, but it's not quite 6. I would say it's a little more than halfway. So I know 5 for sure, because I can measure 5, and then I can estimate one digit. So I might say 5.6 or 5.7 centimeters. Again, I can't just go out and say 5.70428. I can only estimate one place. Now sometimes when you use a calculator, have you ever done that before? Like if you do 24 divided by 7, it might give you a long answer with a lot of decimal places. Well, if you report that answer, that implies that you have measured out to all of those decimal places where all the numbers that you put in were 24 and 7. So you shouldn't have a lot of decimal places for that type of answer. And so that's what significant figures do, is it just makes sure we're not reporting more data than we actually measure. So there's some rules for significant figures. Now when we learn the rules, it seems a little confusing because it seems like what's the point? But in the next lesson video, I'm going to split this one up into 2 lesson videos, this section, since it's kind of long. In the next lesson video, when we learn how to use them in calculations, these rules make a little more sense. All right, so there's 5 rules. So every non-zero digit is significant. All right, and when we say something's non-significant, it doesn't mean we ignore it or it's not there. It just means that we don't need to count it in our calculations. And I'll show you what I mean on the next lesson video. So if I had 254, none of these are zeros, so I underline that they're all significant. You'll see me do that a lot in class, is I underline what's significant. 65.43, none of them are zeros, so I underline all of them, they're all significant. The zeros are the questionable ones. All right, so there's 3 different places the zeros can be. They can be in front of or to the left of the numbers, they can be in between the numbers, or they can be at the end or the right of the numbers. So zeros in between significant figures are significant. So see how I have 3005? So these numbers are significant because of rule 1, they're not zeros. And these zeros are in the middle, so they're also significant. All right, here's another example, 1.083. 1, 8, and 3 are significant because of rule 1, so the zero is in the middle, so it's also significant. Okay, so you'll hear me call them middle zeros a lot. Next one, zeros before or to the left of significant figures are not significant. So again, it doesn't mean they go away, it just means that when we use calculations, we're not going to count those. All right, so if we have 0.07902, well, 7, 9, and 2 are significant because they're not zeros. This 0 is significant because of rule 2. It's in between the numbers, but these zeros before the significant figures are not significant, so I did not underline them. Again, it doesn't mean they go away and this number becomes 7,902. It just means when we do calculations in the next lesson video, we won't count them. We'll still put them in the calculator. I'll show you how to do all of that. All right, and so zeros in front are not significant. They're just placeholders. Or if we have 0.6932, well, 693 and 2 are all significant because they are not zeros. This 0 in front is just a placeholder. It's not significant. All right, and then the last place we can find zeros is after or to the right of the significant figures. So zeros after or to the right of the significant figures are significant only if the number contains a decimal point. Okay, so if you don't see a decimal point, don't add your own. If you don't see one, it does not contain a decimal point. So here, we have 20.3200. Do we see a decimal point? Right there. So the 2, the 3, and the 2 are significant because of rule 1. This 0 is significant because it's a middle 0. And then the end zeros are significant because I see a decimal point. All right, so here we have 63,000. 6 and 3 are significant because of rule 1, they're not zeros. These zeros are after or to the right of the numbers, but I don't see a decimal place. a decimal point. So they are not significant, they are just placeholders. Again, they're still there, they're just not significant. On the other hand though, if I have 570 point, then that 0 after the 5 and 7 becomes significant because then I see a decimal point. So 5 and 7 are significant because of rule 1. The 0 after the numbers is significant because I can see a decimal point. Another time that this comes into play is scientific notation. For scientific notation, don't try to underline anything with the power of 10. Just disregard that. Okay, you're just looking at the coefficient. So I have a 3 and a 1. Those are significant due to rule 1. They're not zeros. This 0 is after the significant figures, and I can see a decimal point. For scientific notation, don't try to take it out of scientific notation. Just leave it in scientific notation and just focus on the coefficient. All right, and then the last one is numbers that can be counted, and conversion factors have an infinite number of significant figures. So for example, if I gave you a bunch of crayons and said how many, you're just going to count them. Okay, so the unit gives away whether it's something measured or counted. So like if you were doing grams, you're not going to count grams, you're going to measure that on a scale. If you're doing milliliters, you're not going to count milliliters, you're going to measure it in a graduated cylinder. But something like crayons, pencils, people, cats, cars, all of those things we would count. So you can't underline, you just write infinity or the symbol for infinity. Or conversion factors, we'll learn more about those in section 3. So like 1 kilometer equals 1,000 meters. Both of these numbers have an infinite number of significant figures. And so again, you can't underline, you have to write infinity. If you just underline all of them, that makes me think you think there's 3. So you look at the unit to decide if you count them or not. All right, so let's look at some examples of this. So it says how many significant figures are in each measurement. All right, so let's look at the first one. What I'm going to do is I'm just going to underline. So 1, 2, 3. Are any of those zeros? Nope. So they are all significant. So for part A, there would be 3 significant figures. For part B, we know because of rule 1 that 4, 5, and 6 are significant because, of course, they are not zeros. But what about these zeros? Well, these are middle zeros. See how they're in between? They're middle zeros. Middle zeros are always significant. So I can just underline all of them, and this one would have 5 significant figures. All right, the next one. Remember, for scientific notation, I disregard this part. I'm not going to take it out of scientific notation. All right, so I know that 9 and 8 are significant. These zeros are after the digits, and I can see the decimal point, so they are significant. All right, so maybe pause the video for a second and try these on your own, and then start it again and let's check your answer. All right, so I'll assume you paused and tried these already. So 22 meter sticks. Now, am I going to count meter sticks? That's like a yardstick, a big ruler, except meters is slightly different than yards. Would you count those or would you measure it? You would count those, like meters, millimeters, meters, 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 grams, I'm going to measure. But this is a number that I would count. So I don't underline in this case. So how many? It has an infinite amount of significant figures. All right, so let's look at part E. We know 7 and 8 are. We know the middle zero is. Front zeros are never significant. It doesn't matter where the decimal is. Front zeros are never significant. This 0 in back is significant because I can see the decimal point. So this one would be 4 significant figures. All right, part F is 98,000. We know the 9 and the 8 are significant. These back zeros, they could or could not be. Do I see a decimal point? No. If there's no decimal point, it's not significant. All right, and then last one's 170 grams. So we know that 1 and 7 are. The 0 after could or could not be. I can see the decimal point, so it is significant. And see, these are the two that people struggle with because they're like, why, just because you put the decimal point there, does that make this significant and not these? Why can't I just put a decimal? Okay, it's all about how you report your data. When they reported their data, they did not measure these places. They're just placeholders. They weren't measured. Since they put their decimal there, that's showing we literally measured through the ones position or through this 0 right here. That's all it's saying. Like I said, it's just about reporting accurate data. All right? And so there are my answers. So, again, maybe pause the video and you try these real quick on your own. I'll assume you paused it and tried it, and now let's look at them together. All All right, before we start meters, meters, and grams, I would measure all of these, so none of these are going to be infinity. So let's look at part A. Because of rule 1, 5, 7, and 3 are significant because they are not zeros. Front zeros are never significant. This back 0 is significant this time because I can see a decimal. All right, so you should have gotten 4 or underlined 5, 7, 3, and 0. All right, part B, 8765 meters. This one should be easy. None of them are zeros, so they are all significant, just like that. Hopefully you're getting these right. For part C, we have 0.00073 meters. So I know the 7 and the 3 are. What about front zeros? Front zeros are never significant. Okay, front zeros are never. It doesn't matter where the decimal point is. All right, and then we have a scientific notation one. So remember, don't worry about the scientific notation, just worry about the coefficient. So 8, 7, and 5 are significant. We have a 0 in back, so a 0 in back is significant if I can see a decimal place, which I can. I mean a decimal point, sorry, which I can. All right, and so if you wrote numbers instead of underlining, you would have gotten 4, 4, 2, and 4. All right, so hopefully you did well on that. So we're going to stop here for our first part of section 1, and if you want to continue, there will be a part 2 to this section to finish up with the significant figures and calculations.